Hello everyone, I'm Jorge Gacitua Gutierrez, and today I'm sharing part of my PhD research. My work focuses on mitigating the impact of nonlinearity in the observation operator using the transform Kalman filter approach. As you may know, the relationship between radar reflectivity observations and the model state variables, such as the condensate, is nonlinear. This nonlinearity can degrade the performance of Ensemble Kalman filter. So, based on the work of Kurosawa and Potterjoy, iterative approaches can help to mitigate these nonlinear effects. In this research, we aim to evaluate the performance of iterative methods for nonlinear observation operators, starting with a simplified model and showing preliminary results with a state-of-the-art atmospheric model, which is WRF. In the iterative of temperate ensemble Kalman filter, at each assimilation cycle, we assimilate the same observation several times. So to be consistent with the optimal formulation of the Kalman filter for linear systems, observations are assimilated gradually by inflating the observation error covariance. This observation error covariance inflation factor should follow this expression for consistency. This is equivalent to perform a factorization of the observation likelihood. The advantage of the iterative approach is that on each iteration, nonlinear observation operator can be linearized around the state that is closer to the true state. We perform a first set of experiments using the Lorentz 96 model with 40 variables and a forcing of 8, a widely used standard configuration. In our experiment, we use a nonlinear observation operator. This operator is inspired in the relationship between radar reflectivity and concentration of large water condensate within cloud. When X exceeds a certain threshold, we assume that we have a cloud, and the observation is a nonlinear function of X. When X is below that threshold, the observation is equal to 0, meaning that we have no clouds. Additionally, in the polar view animation, the true state is represented by line, with reflectivity-like observations appear as dot. In this setup, all model state variables are observed. We assume Gaussian and uncorrelated observation errors. Despite the simplicity of the model, we observe complex or chaotic dynamics. Regions with high reflectivity-like values resemble isolated convective cells, which undergo cycle of development, dissipation, and displacement. Some move it quickly, while others persist in the same location. In these experiments, we use the local ensemble transform Kalman filter. Each realization of the experiment consists of 1,000 data assimilation cycles. To assess the impact of temperate elliptic EF, we first establish a baseline using the standard elliptic EF and compare it with the iterative implementation using 2 and 3 iterations. For a more fair comparison, each experiment is repeated across a range of localization scales and multiplicative inflation factors. As in Kurosawa and Potterjoy, in all the experiments, the model is assumed to be perfect. In this first set of experiments, we explore the sensitivity of the iterative elliptic EF to the number of iterations and to the observation error variance. Here in the first column, we see the elliptic EF. In the second column, we see the elliptic EF with 2 iterations, and in the third columns, we see the elliptic EF with 3 iterations. And in the different rows, we see the different observation error variance. The result shows that first, the temperate elliptic EF tend to stabilize the filter, avoiding filter divergence. The minimum root mean square error over all localization and inflation combination is lower with the temperate versions compared to the normal or the standard elliptic EF. But performing 3 iterations does not show a clear advantage over performing only 2. In some cases, additional iterations lead to degrade the results, which is this case. And the impact of tempering is particularly important when observation errors are small. For larger observation error, the percentual improvement in root mean square error between the LTKF and the iterative LTKF decreases. The amount of information assimilated at each iterations can be adjusted as long as the value of alpha used at each iteration meet the constraint. Different ways to define this alpha at each iterations are possible, from uniform alphas to a distribution that seeks to start assimilating a relatively small part of the information in the first iterations and then increasing the amount of in the following step. So we use exponential functions to achieve this type of distribution for alpha and test the sensibility to this coefficient that control the size of each step, specifically this alpha S. We use a more challenging scenario to investigate the sensitivity to the selection of the alpha. In this scenario, only half of the observations are assimilated, and the assimilation frequency is reduced to 1 every 12 time step. And the observation error variance is fixed at 5. The use of the tempered LTKF is positive in this challenging scenario, similar to what we previously see. In this figure, again, we see after the first column the normal LTKF, and in the second column the LTKF with 2 iterations, and in the third column the LTKF with 3 iterations, and now the rows show different values of alpha, from alpha 0 to alpha 3, and for example in the alpha 0, in each, for example, at alpha 0, at each iteration step, the correction is the same. The use of the tempered LTKF is positive in this challenging scenario. The use of a uniform iteration step produces a good result in terms of error reduction, but the use of a smaller step at the beginning and larger step afterward produce even better results. One possible reason is that at the first step, the linearization of the observation operator is not accurate, so assimilating a large part of the information under this condition is suboptimal. By reducing the analysis update at the first step, we can improve the linearization of the observation operator for the following step, leading for better results. Again, in this figure, in the first column, we see the normal LTKF. In the second column, we see the LTKF with 2 iterations. And in the third column, we see the LTKF with 3 iterations. And in the different rows, we see the different ensemble sizes from 10 to 20, 40, and 100. The results shows that the positive impact of tempering can be found for all ensemble sizes, since increasing the ensemble size do not help to avoid the detrimental impact of non-linear observation operators upon the performance of the filter. The impact of the number of iterations is more consistent for larger ensembles, and the optimal localization scale is larger as the number of iterations increase. This could suggest that the iterative filter is able to make a more efficient use of distant covariance. Then we want to analyze the potential impact of the tempered LTKF in a more realistic scenario. We perform some idealized experiment using a trained member ensemble generated with the work model. The ensemble simulation corresponds to a case of a large mesoscale convective system in Argentina, and is downscaled from a GSF ensemble. One of the ensemble members is assumed to be the true state, while the rest will be used as the forecast ensemble. The black horizontal line indicates the location of the cross-section at which we analyze the impact of assimilating. For this case, we consider 3 scenarios, one in which the ensemble member showing the lowest reflectivity value the observation location is selected as the true state, other in which the ensemble member has the higher reflectivity is selected as the true state, and other in which the ensemble member is closer to ensemble mean. This figure shows the vertical cross section for each of the cases, and also the ensemble mean of all 30 members. In the following slides, I will show you the results of assimilating a single reflectivity value for the Graupel concentration and the vertical velocity. The first variable is directly related with the reflectivity, while the other are updated through an estimated covariance. And in the first column, we see the LTKF, then we see the LTKF with 2 iterations, and then the LTKF with 3 iterations. In the first row, we see the forecast. Then we see the forecast minus the analysis. And finally, we see the error, which is the analysis minus the true state. And also a calculation of the root mean square error in all this area that is shown in this figure. So we see that the analysis update reduced the overestimation of the Graupel in this case, and the iterative approach improved the accuracy around 12%. But with 3 iterations, you cannot see a significant improve beyond the 3 iterations. Now, for the vertical velocity, again, in the case where the observation is below the ensemble mean, we see that also we have a positive correction in all the cases, but with the LTKF with iterations, we reduce the upward motion because we need to have a lower Graupel concentration. And in these cases, the iterative LTKF reduced the analysis error around 22%. And again, the LTKF with 3 iterations does not show any significant improvement. In this table, we see a summary of the 3 scenarios and the different variables that we use during the assimilation. In the first column, in which scenario we see the LTKF, root mean square error, and in the other columns we see the difference between the iterative LTKF and the normal LTKF. First, we see that the case that we show, when the observation is farthest below mean, is the best scenario, and also the variables that we show has the best improvement between the iterative LTKF and the normal LTKF. When it's closest to the mean, we still see some improvement, at least in Graupel and rain. But in temperature, we see an increase in the root mean square error for this case. And in the case that is farthest above the mean, it's not clear that it's a good scenario to use the iterative approach, because we have a very large root mean square error in the iterative methods. One thing that we can say is that in the scenario where the observation is the farthest below mean, also is the case where the difference between the observations and the mean is larger, because even though the farthest above mean is also the maximum reflectivity in all the members, the difference between that point and the closest to mean or the mean of the ensemble is not that far. So in this case, where the difference between the observations and the ensemble mean is where the iterative method is best. So finally, as conclusion, we can say that the tempered LTKF can improve the filter stability and reduce the analysis error by mitigating nonlinear effects in the observation operator, especially when the observation error variance is small. The first iteration of tempering provides the most significant improvement, while additional iterations have a smaller impact. The advantage of the iterative filter depends on the observation error, the sample size, and the observation density. The iterative LTKF outperforms the LTKF in all the scenarios considered. In a more realistic experiments, the temporary LTKF improved the analysis of condensate concentrations, wind, and temperature. Finally, this preliminary experiment suggests that the impact may depend on variable choice and the distance between the ensemble mean and the observation. So the next steps are further sensitivity analysis to investigate how different observation densities and error variance impact on the temporary LTKF performance in different simpler and more realistic experiments. And also extend the study for different alpha values and iteration numbers to optimize the method. Also perform cycle experiment using WRF LTKF radar data assimilation system and investigate the computational efficiency. Compare LTKF versus the tempered LTKF to see how good the impact is and compare it with how much cost it takes to compute an additional LTKF step at it assimilation window. Thank you very much for your attention. And if you have any question or would like to discuss this method further, please feel free to contact me at the email that you can see in this slide and also in the previous slide. So again, thank you very much for your attention.